Welcome to the Strategic Energy Group Building Operator Smart Series. This video teaches you how to manage the cost of good indoor air quality. For additional energy saving tips for your buildings, be sure to subscribe to our YouTube channel by clicking on the subscribe button. My name is Dusty Farrell and I'm an energy coach with Strategic Energy Group. Like previously stated, these are the 4 common opportunities found for reducing energy in your commercial building. Number 1, equipment scheduling. Number 2, appropriate use of outside air. 3 is simultaneous heating and cooling. And last, sensor air. In this video, we're going to take a deeper dive into appropriate use of outside air and discuss ventilation and indoor air quality. During the last video in part 3, I went over the 3 primary reasons for using outside air. Do you remember what they are? The first is free cooling, and the topic of today's video, ventilation and indoor air quality. And the third is building pressure. This is what I'll cover in the next video, part 5. So why do we need to ventilate our buildings? Well, this is to manage the indoor air quality, and we perform this by bringing in fresh outdoor air to dilute and flush out the indoor air pollutants. Now, what are some common pollutants in buildings that contribute towards poor indoor air quality? Can you think of some? Well, here's one: building materials such as carpet and adhesives do. How about office equipment? There's another one. And why is that? Well, these are man-made materials and they have chemicals in them, and the chemicals are constantly off-gassing. This gas is referred to as a volatile organic compound, or a VOC. How about paint? Well, can you think of some more yourself? Just about any man-made material in buildings will release these VOCs, and it would be unhealthy for the occupants if it were allowed to build up. In addition, another big contributor is the building occupants. Now, why is that? Well, it's because people are consuming oxygen and we convert it to CO2. Now, if the CO2 level, those gases, and all these particles were allowed to build up, the indoor air quality will significantly degrade, and the occupants can experience a number of negative effects as a result. So to minimize adverse health effects from these pollutants, the intake of fresh outside air is designed into our building's heating, ventilation, and air conditioning systems. But while the use of fresh outside air is needed to maintain good indoor air quality, we also need to recognize the added energy penalty for over-ventilating the building space. And this is because using fresh outside air does place an additional load on our building's heating and cooling systems. This is especially true during the hot and cold months. Simply put, we only want to provide enough fresh outside air to meet the building's occupied prescribed ventilation rate, or the PVR. The PVR is what I'll be referring to throughout this video. So to answer the question of what it would cost extra to heat and cool only 1,000 cubic feet per minute of fresh outside air per year using that above scenario, if we do the math, you can see that it really adds up. Now, this energy penalty is stemming from the outside air damper getting out of calibration, or it was simply set higher than the PVR. But here is the good news. This energy penalty can be significantly reduced and is even avoidable when routinely verified and adjusted back to the PVR. Before I get to verifying and the calibration of the outside air damper, I want to briefly review how the PVR is calculated for setting the minimum outside air damper position when a building is occupied. Now, to determine this, Engineers will commonly refer to the American Society of Heating, Refrigeration, and Air Conditioning Engineer Standard 62.1, also referred to as ASHRAE 62.1. Now this is a technical reference, and it is really comprehensive, and it's written in a mandatory language so as for easy adoption into state and local codes. But for you building operators that are watching this video, I encourage you, I want you to become familiar with this reference so you'll gain a better understanding of the general criteria that engineers are using in calculating the PVR for your building's HVAC equipment. To get you going, let's cover the 4 main criteria used for calculating the PVR. The first is the building's space use. We need to define this because there are lookup tables that provide multipliers for the building use type. For example, gymnasiums will typically require a higher rate of ventilation versus a standard office building. So each type of space usage will have a unique multiplier. The second is how many occupants will occupy the given space at any one time. The next one here is the total size of the space that's going to be ventilated, typically referred to as conditioned floor area. And the fourth is the supply fan's capacity in CFM. So now that you're armed with this information, I encourage you to further your knowledge and become more familiar with the ASHRAE Standard 62.1. Also, you might try to acquire your building's occupied prescribed ventilation rate by going to the individual fan systems installation and commissioning documentation. Now let's say the outside air damper is commanded to its minimum ventilation position based on the PVR. How do we really know if we're not overventilating? Now that's the question here. And to know this requires measuring the amount of fresh outside air being drawn by the fan system. And this can be performed by a number of methods. The preferred method is for a certified test and balance technician to take measurements using test instruments and then comparing the flow to the PVR. The technician will then make the necessary calibration and adjustments. In some installations, you might find the fan system's outside air inlet is equipped with an airflow station. This type of method provides instantaneous feedback and is a great way to compare flow to the PVR. In some applications, you might also find a dedicated outside air damper that's been specifically sized to meet the PVR. This damper will be smaller in size and is not part of the economizer configuration. And since this damper is not used for free cooling economizing, it only has 2 positions, and they are 100% open when the building is occupied and your fan is on, or 100% closed when the fan is off. Another method is a simple calculation that you can perform that provides the percentage of outside air being drawn into the fan system using 3 common temperatures that are found at the fan system. And those 3 temperatures are the outdoor air temperature, return air temperature, and the mixed air temperature. If the fan system is controlled by an energy management system, chances are it is monitoring these temperatures. If it doesn't, you'll have to manually measure them yourself. To calculate the amount of outside air being drawn in as a percent of total, be sure to write this formula down. Return air temperature minus the mixed air temperature divided by return air temperature minus the outside air temperature. Multiply the answer by 100 to get the percentage value, and this equals the percent of total fan airflow coming from the outdoors. I'll give you a word of caution on this one. This calculation works best with at least 10 degrees temperature difference between the return air and the outside air temperatures. And the reason for this is the closer the two values get, the more the error will get exaggerated. I like to take these readings early in the morning when there's plenty of difference between the two sensor values. Now, since I think it's so important to verify if a fan system is overventilating, let's go over how to easily calculate and verify the actual percentage of outside air. So in this example, we have a return air temperature of 68 degrees and a mixed air temperature of 53. 68 minus 53 equals 15. Then we have the outside air temperature of 52. 68 minus 52 equals 16. Then 15 divided by 16 equals 0.93, and we will multiply that by 100 to convert to a percentage, and this equals 93% of outside air. Now, that wasn't too complicated, was it? I encourage you to post this calculation near your energy management system for later reference. Now, I want to do this one more time, but only to demonstrate one other important point. In this example, we have return air temperature of 72 and mixed air of 65. 72 minus 65 equals 7. The outside air temperature of 52, so 72 minus 52 equals 20. Then 7 divided by 20 equals 0.35, and multiplied by 100 equals 35% of this fan's total airflow is fresh air coming from the outdoors. But let's compare that calculated percentage to the displayed percentage value from your energy management system, or maybe you call it the BAS system. And here we see that the outside air damper is commanded to only 25% open. So the question here is, why is there a 10% difference between the two percentages? Well, this is due to the energy management system's displayed outside air damper value of 25% is merely a percent of open from 0 to 100%. I want you to keep in mind that airflow through a damper is not always linear. The commanded position does not necessarily represent the actual airflow percentage across that damper. So even though the outside air damper may be commanded open 25%, the actual percent of outside air being drawn can significantly be higher or lower. The point being, when the EMS has commanded the outside air damper to its minimum ventilation set point, you can't automatically perceive the displayed value percentage as the actual position. My recommendation is to use one of the previously mentioned methods that measures the actual flow and then compare it to the EMS's displayed percentage. Then adjust the EMS's minimum ventilation set point as necessary. I've been talking about air handlers, but a special note about RTUs, which stands for rooftop units. These units are oftentimes the HVAC little workhorses for your small to medium-sized buildings, usually providing both heating, cooling, as well as ventilation. RTUs may or may not have an outside air economizer damper on them. This would be frequently a matter of their age and size, although nowadays most building energy codes do require that RTUs be installed with economizers. But this was not always the case for those older units. And these poor things do sit out in the weather all of their lives. They're out of sight and they're out of mind, and oftentimes forgotten and ignored. It's no surprise that we find approximately 1/3 of the economizers on these units are not even functioning properly. Due to my limited time, I'm not going to be discussing RTU economizer performance, but if you do have an indoor air quality issue, you can apply the same principles and investigate the outside air damper. This concludes video 4 of this 8-part series. I hope the information reinforces what you already know or enlightens you to a better understanding a building opportunity assessment. In part 5 of the next video, I will cover the appropriate use of outside air that's used for maintaining proper building pressure. So won't you join me then? And remember, for additional energy saving tips for your building, please subscribe to our YouTube channel by clicking on the subscribe button.